description of the worksheet today. I don't have that today. It's kind of hard to work with him sitting there. He has, I want to stop and drop and do whatever he needs me to do or my mother needs me to do. So I got interrupted over and over again. So I couldn't really focus and sit down and work on what I'm supposed to work on. But I'm hoping Tuesday that I'll have a nice worksheet with a algorithm for you of what's expected for the final project, detailed in pieces with a rubric and everything. So I just wanted to remind you, we're going to do mostly in-class assignments today because last time I did more talking and you can't see anything because I don't have anything up.
And so you like an app like that.
What the heck is this? This thing, I move it over.
In case you have any secrets or something.
Huh?
Any secrets that you're trying to hide. Probably for like a glare. Did you see all the dust particles that just popped up?
Scary, right? Our clinic is right over there without anything. So recall, if this shows up, here we go. Slow. There we go. Oh, there we go. Okay, recall that we worked on this theorem last time. It's the Sprague-Grundy theorem, which says that the Sprague-Grundy function of a sum of games, so graph games, is equal to the nim sum of the Sprague-Grundy points of each individual game. So I just wanted to remind you about this theorem. You might want to jot it down because your in-class assignment requires this formula right here. So that means if I'm giving you a position from game 1, that's x1's a position in game 1, and x2 is a position in game 2, and so forth. The Sprague-Grundy function of that n tuple is going to be equal to the nim sum of the Sprague-Grundy functions of each individual guy. And do you recall how to calculate the nim sum? How do you do that? What do you do? Give it to me step by step. Step 1. Binary expansion. And then next, write each number into binary expansion. Next step? Add them, right? Make sure that if they're all lined up, and what if one number doesn't have enough ones in it, or you can't add it together? What should you do? Front end it with a bunch of zeros, and then add them together, mod 2, and that answer that you get, you recast that back into base 10, and that is your nim sum. That's the definition of the nim sum. Okay, so we're going to figure out what this is good for. So the first thing I'd like you to do is, we've done this before. Let's look at the nim pile of where we have a nim pile. So it's multi-pile. We have 9 tokens, 10 tokens, and 14 tokens. I'd like you to find the directed graph and the Sprague-Grundy function for each pile. So in the recall that what you would do is you take the pile and consider that one pile as a single pile. What is the subtraction set going to be if you have 9 tokens written out? What are you allowed to pull from that one pile in the game of nim? 1 through 9. So your subtraction set is going to be 1, 2, 3, 4, 5, 6, 7. So now you're going to have to make a directed graph for that n pile. And recall that the Sprague-Grundy function is recursive, so you need the whole thing. You start out at the bottom. The Sprague-Grundy function at position 0 was 0. The terminal point was 0. And the next point that leads to the 0 is 1. So you know the first 2 points, and then you go from there and lead up to the Sprague-Grundy function. So you did this already for the subtraction set 1, 2, 3 with 10 tokens laid there.
Isn't everything a winning position? Isn't everything a winning position?
Let's see.
The set is 9 to
See what happens, right? You had to put the winning positions, and then you had to do the Sprague-Grundy function. So the first comes the losing and winning positions, then comes the SG function. So figure this out now for 9, 10, and 14.
So for the 10, 14, are we taking subtraction set? Or
It would, right? What would you be allowed to take from a subtraction set with 10 tokens in it? Right. So if you don't have a partner, line up with a partner. No partner. Find a partner. You can join, maybe, Teresa, you play with having 3 in yours? Right. There you go, right up there.